Hi, I'm Hermine Maas, and this is the second part of the OpenMX script that was used in Day 3's Practical of the Boulder Workshop 2022 that deals with genotype by environment interaction models. These build on the heterogeneity models where we compare whether the variance components can be constrained across two groups, such as males and females. But now we're looking at whether the variance components are actually equal across the range of a continuous variable, in this case, age. So here we're using the twin data again that comes with the OpenMX package. So assuming you've already loaded OpenMX, we can then load the data and select the variables of interest. And those are again BMI, but in this case just for females, but across the whole age range from 15 to about 80 years of age. So we select zygosity codes 1 and 6 for the MZs and 3 and 8 for the DCs. We can look briefly at the descriptive statistics. And again, we have a mean of about 21 and a variance of about 0.9 for this measure. We set some start values. And then we move to the main part of the script, where now, in addition to moderating the variance components by age, we are also including age as a covariate on the mean. And in this case, we even extend it from regressing out the linear effects of age to also including the potentially quadratic effects of age on the phenotype. So what we do at first is define two definition variables, one called defHL and one called defHQ, where we have previously generated an age variable that's divided by 100 and then multiplied it by itself to generate the square of age. And those variables are included in these two matrices here that we then multiply with their respective regression coefficients using the algebra in mean age that multiplies the B matrix, which is now a 1 by 2 matrix, with a 2 by 1 vector of the age and age squared data in your sample. So the expected mean is again the sum of the intercept and the regression on not only the linear, but also the quadratic effects of age on BMI. Now here, as indicated in the theory lecture, for the G by E models, we're not using the direct variance estimation approach because it doesn't extend to these types of models. At least we have not found a solution that's completely equivalent. So we're going back to using the path coefficients approach. So instead of directly estimating the variance, what we're really estimating is the square root of each of the variance components. And those are specified in these three matrices here that we now call path A, path D, and path E, and which I've given a lowercase name, little a, D, and E, because to obtain the predicted variances, we are going to multiply that matrix, these three matrices, with their transpose to get the squared matrices, which we call big A, D, and E in the next three lines here. So let's run those. And so these big A, big D, and big E matrices are actually equivalent to the VA, VD, and VE matrices we've estimated in the direct variance approach in terms of their estimates. We then generate the expected covariance here in CovP by just adding the three variance components. And now we have a different set of A, D, and E path coefficients that are being defined. Because if you recall the path diagram for the G by E model, we are now going to see whether part of the genetic and environmental variance is moderated by age. And we do that by estimating a separate parameter that captures this moderated effect of the A, D, and E components. So that's why we call them AI, DI, and EI. I stands for interaction with age in this particular case. Now then, to get the overall predicted variances, we get a slightly more complicated algebra expression because we add the effects of the unmoderated components to those of the moderated components. And you see that these are moderated as we've multiplied each of the components that have the I, the interaction in them, with the definition variable for age. So if you work out this algebra, you see now that not only will the result be A squared plus HL times AI squared, but also twice their covariance, because it's the same set of genetic factors that can have both an unmoderated as well as a moderated effect on the phenotype, where the moderation is through the age variable. So let's run that part too. And then our expected covariance matrices for the MZs and the DZs are then simply the AI plus DI again for the MZs, and a half AI plus a quarter DI for the DZs. And this these expressions are becoming more familiar to you, I'm sure. We then, of course, have to put the data back into an MX data object and generate the MX expectation normal statements with the correct expected covariance matrices and the correct expected means matrices. We are then going to generate the two models, one for MZ and one for DZ. And again, as stated before, when we have definition variables, we are going to put all the matrices that are the definition variables or functions of those definition variables in a separate list from the other parameters. So we have parse for the parameters that are not multiplied by a definition variable, and defs for the ones that involve a definition variable. The reason why we do that is that when we specify the models here, you see that it includes both the parse and the defs lists of variables. But if you go further down and look at the overall model, that only includes the parse object, because the definition variables, the actual variables, are only in the MZ or DZ specific models, and so would not be able to be included in that overall model. So there we go with that part of the model. Now, here you see a little bit more algebra. And of course, this is not necessary as part of running the main G by E script, but it makes it a little bit easier to then generate the summary data and tables that one might be interested in. And given that we may want to estimate some confidence intervals around derived parameters, we have to calculate them as part of the model, which is exactly what we do here. The top part here is familiar to you. It's just a matrix that includes the unstandardized and the standardized variance components. But remember, in here, these are just those based on the unmoderated effects. So only in the situation where the three moderated parts, AI, DI, and EI, are not significantly different from 0, can we use just one estimate of the predicted additive genetic dominance and unique environmental variance. And that's what we would get from this part of the model. If the moderation is significant, It means that each of the variance components now change as a function of the moderator. So there is no longer just a simple estimate of the additive and the dominance and the unique environmental variance component, but rather we now can predict the magnitude of these three variance components as a function of specific values of the moderator. And so we know that the moderator in this case age is between about 15 and 80 years of age. And so what we're going to do here is generate a little table that works out what the predicted variances are at those at specific values within that age range that we have for the moderator. So in this particular case, I've chosen 7 levels, and I'm going to work out what the predicted variance is at age 15, 25, 35, all the way up to 75. And remember that we had age divided by 100, which is why we have the predicted values also divided by 100. But of course, we should interpret that in terms of age 15 through age 75. And we do this with a variety of algebra that I'm sure you can work through on your own time to see exactly how this is done. So the calculations are happening in this part of the script. And in the next part, we then generate some labels for the rows and columns of this table that we're generating. And we generate 2 different tables, one that has the predicted variance components, but also the predicted means as a function of age that are unstandardized. And we also work this out for the standardized variance components, so we can see the difference between what these 2 types of summaries will provide to us. So this generates those 2 tables, and all the elements are in this list called prop age that we include as an argument of our overall model so that it becomes evaluated as part of the model. We can also generate confidence intervals around these moderated parameters, and that will allow us to plot not only the point estimates for the moderated and unmoderated variance components, but also their confidence intervals. Okay, so let's do that and start running the model. Now, even though we only have 9 parameters, and you can think through what these 9 might be for a second, you'll see that this takes considerably longer because we're, in addition to these 9 parameters, we're asking for quite a few confidence intervals, not only of these parameters, but also of these parameters at specific ages. And that requires a lot more optimization. So whilst that is still running, let's think through the 9 parameters. Remember, we had the intercept of BMI. Then we have the regression on age and the regression on age squared. So that's 3 parameters. And then with respect to the variance components, we have both 3 unmoderated variance components, A, D, and E, or actually it's little a, little d, and little e that are actually estimated and that are then squared to get the variances. But we also have little a I, little di, and little ei as the moderated variance components. And it looks like the model just finished running, so we can explore the output. First, we get the goodness of fit statistics. And of course, we would normally also fit a saturated model to see if this model fits the data reasonably well. But let's have a look at the estimates. And so these are the raw estimates that we actually are optimizing in this model. And as you see, we have the intercept and the regressions on age, and then the unmoderated and the moderated variance components, and a range of CIs. Now, it might be easier to present those in a slightly different way. And so these are CIs around certain columns of these two tables. First, we have the table UXH, which is the table of estimates that are unstandardized. So these are the raw estimates of how the variances AI, DI, and EI change as a function of age. And in this case, we've plotted this for age 15 all the way through age 75. And we've also included the predicted mean that goes, that increases slightly with age or age squared. And then you see that the additive genetic variance component actually is fairly stable, but decreases slightly from age 15 to age 75. The dominance variance, however, increases quite dramatically, but that is even more so the case for the unique environmental variance that increases from about 0.14 to about 0.49. Which results, of course, in an increase in the total variance, which is the sum of the three components AI, DI, and EI. Now let's see what this does for the standardized variance components. So a similar kind of table, but now for each of the ages, if you add up A squared, the AI column with the DI column and the EI column, you see that they will all add up to 1. The total variance, however, as we know from the previous, is just copied from the previous table, goes up quite a bit. And so it may be not so obvious here, but it may provide a quite different kind of picture to how these variance components change with age. And it's probably easier to show this in a plot. So that's exactly what we'll be doing next here. So again, here we use R's capabilities to generate plots, and we generate both a plot of the unstandardized variance components and one of the standardized variance components in this first part of the script. Oh, of course, what the script is actually doing is generating the plot and saving it as a PDF, but we can show it here as well. I think if I generate the plot commands, and here we go. It does print it a little bit off as far as the dimensions of the graphs, and I'm sure there are people that can fix this so that it shows up as expected right away. So on the left here, we have the unstandardized variance components. And as I was saying, this is basically just using those values in the table in this plot here. We had a huge increase in variance of BMI that is primarily accounted for by the yellow line here, which represents the unique environmental variance, and to a lesser extent by the dominance genetic variance. But if we look at the unstandardized estimates, you see that actually there isn't an increase in the additive genetic component. It is pretty stable. However, if we had plotted the standardized variance components, then it appears that the additive genetic variance goes down significantly with age, whilst the other two sources of variance go up. But of course, that's a little bit of a distortion of the reality, as we know that the additive genetic variance actually doesn't change when we look at the unstandardized parameter estimates. In the next part here, I used all the confidence intervals that were generated here and rearranged them in a table similar to what we did for the other variance components, as you can see here. And the reason I reorganized them was that that would make it easier for me to plot the data. Now, I'm sure that one of you can find a more elegant way to generate the plots that include the confidence intervals, which I'm doing in this latter part, and I'm going to not include the PDF, but generate it right here. And again, I get this a bit distorted picture, so let's try to make it look a little bit more like what I was expecting. So here we now have separated out the 3 variance components, because it gets a bit messy when we try to add in the lower and the upper confidence intervals, the LCI for the lower and the UCI for the upper confidence interval. And of course, the actual curves for the point estimates of these 3 variance components is the same as what we have shown in the previous slide with the unstandardized variance components. But now we added in the confidence intervals, and you see that in each case, the confidence intervals widen gradually with age. This is actually a function of the sample size of the sample that is primarily of a younger adult age. So we have a lot more people in the 20 to 50 range than above age 50. But the other thing that we notice is that the confidence intervals around the additive genetic and the dominance genetic variance are substantially larger than the E component. Again, this is a pattern that is to be expected, because we know the estimate of the unique environmental variance with a lot more precision than we do the additive and the dominance component. And furthermore, the additive and the dominance components are correlated, so you end up with pretty large confidence intervals across this whole age range. Now, of course, the logical question in these models is, are these trends with age actually significant? In other words, is there significant moderation of these variance components, or are these estimates really not different across this age range? So typically what we do then is fit a submodel where we fix the moderated components to 0, and so then end up with just one single estimate of A, D, and E for this particular phenotype. So that's the first submodel that we can fit right here. Now you see that I compare this model with the full model that had the 9 estimated parameters. This one has 6, because we're testing the unmoderated, the moderation of the variance components at the same time for A, D, and E. So it's a 3 degree of freedom test. That looks to be highly significant here. Of course, given that we find a significant moderation of the 3 variance components doesn't mean that all 3 change significantly with age, and one could go a step further and test separately whether this is due to a change in the additive genetic, dominance genetic, or unique environmental component. Now, if there is no moderation of the variance components, we could then also further test, of course, whether our moderator age in this case also has a main effect that is either linear or quadratic. So the next 2 submodels in this case drop from this unmoderated model the quadratic component first, and then the linear component. And then we can compare all the models with this last MX compare statement. And in this case, all 3 of these models have significant p-value, indicating that we have not only a main effect of age, a quadratic effect of age on body mass index, but also that the variance components that account for the variance increase in age change significantly across the adult age range from about 15 to about 80 in these female twin pairs. And the phenotype that we've been analyzing here is body mass index, a measure of body composition. Thank you very much.